Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we studied the definition of system and understood different types of interconnection. And also we studied two of the six important properties of the system, namely memory and invertibility. A system is said to be memory system if the output of the system depends on present input as well as past input. And a system is said to be memoryless system if the output of the system is dependent on present input only. Likewise, a system can be invertible or non-invertible. A system is said to be invertible system if we can recover the input back from the output. By applying the output of the system to a suitable inverse system, if we are able to recover the input of the first system, then a system is said to be invertible system. And the system that is used to recover the input back is said to be inverse system. In today's lecture, we'll continue our discussion on the remaining four properties of the system, and at the end we'll solve a couple of problems to understand these properties. The first system property we'll be studying for the day is called as causality. A system can be causal or non-causal. Causal systems are non-anticipatory and they are realizable in real time. Non-causal systems are anticipatory and they are non-realizable. Usually non-causal systems are non-real-time systems. Will not be able to realize them in real time. A system is said to be causal if the present value of the output signal depends only on the present or past values of the input signal. This definition is pretty similar to the definition of memory system. System output depends on present as well as past values of the input. For memory system, compulsorily the output of the system should depend on both present as well as past values. But for causal systems, output of the system shall depend on either present value of the input or past value of the input. Then a system is said to be causal system. In contrast, if the output signal of the system depends on future values of the input, then a system is said to be non-causal system. Meaning we should be predicting what will be the input signal in future time. Therefore, non-causal systems are anticipatory. Because we need to predict what should be the input in future time, these systems are generally non-realizable systems. So the definition for causality is a system is said to be causal if the present value of the output signal depends on present or past values of the input signal. In contrast, the output signal of a non-causal system depends on one or more future values of the input signal. And system S is said to be causal if and only if, suppose we have two inputs, x1 of t and x2 of t applied to two different systems or applied to the same system, and both the input signals are same for time instant less than t naught. And if the output due to these inputs x1 and x2 are also same for time instant less than or equal to t naught, and after t naught one of the system output is linearly rising and another system's output is exponentially rising. Basically, after t equals to t naught, both the systems will not behave same. They'll be varying differently. So a system is said to be causal if input-output behavior is same for all time t. To understand this, let us consider an example. a system defined by y of n equals to 1 divided by L summation k equals to minus m to plus m x of k, where L is equal to 2m plus 1. Now this system is causal for n greater than m, and it is a non-causal system for n less than m. Therefore, if a system is causal, then it must be causal for all conditions. Therefore, the defined system y of n equals to 1 divided by L summation k minus m to plus m x of k is a non-causal system, because it is causal for some range of n and it is non-causal for another range of n. So if a system has to be causal, it should be causal for all the values, all the conditions. Then a system is said to be causal system, else it will be a non-causal system. The second property we'll be studying is called as stability. Now I'm sure you must have studied different definitions of stability in your control system subject. In this subject, because we'll be dealing with signals and systems, we'll define stability with respect to input signal and output signal. A system can be stable system or unstable system, and the stable system's definition with respect to input and output is: a system is said to be bounded input, bounded output stable if and only if every bounded input results in a bounded output. So for a system, if the input is bounded, system should also result in bounded output. Then only a system is said to be BIBO stable, or bounded input, bounded output stable. If the bounded input produces unbounded output, then a system is said to be unstable system. For example, y of t equals to e to the power t. A system is defined by this equation: y of t equals to e to the power t. If the input to this system is x of t equals to u of t minus u of t minus 1. U of t minus u of t minus 1 is a bounded input. If this input is resulting into an exponential output, y of t equals to e to the power t, because t is unbounded, y of t equals to e to the power t will also be unbounded. So it is an unstable system. Bounded input is resulting unbounded output. So it's an unstable system. Y of n equals to summation k minus infinity to n x of k. Now for each of these systems, the condition is input has to be bounded, and that bounded input should result into bounded output. So to define those bounds, modulus value of x of k, the input, should be less than or equal to some value m, which should be less than infinity. Then only an input signal is said to be bounded signal, and this should be true for all time instants, for all values of k. And sometimes, even if input is bounded, output y of n can go unbounded. So system can be unstable systems. So for stability, these following two conditions are very important. Mod x of k should be less than m, which should be less than infinity. Then only an input signal is said to be bounded for all values of k. For this input signal, output whatever we get should also be bounded, which is defined as mod y of n should be less than or equal to m of a, some value. It should be of finite value, which should be less than infinity for all values of n. Then only a system is said to be bounded input, bounded output, stable. Let us consider one more example. Y of n equals to 1 divided by 2l plus 1 summation k minus l to plus l x of n minus k. X of n minus k should be bounded, meaning it should satisfy the condition modulus value of x of n minus k should be less than or equal to some finite value m. Then y of n, if it is exactly equal to when m is equal to l, then y of n will also be having a finite value. Then a system is stable system. Let us consider one more discrete time system defined by y of n equals to 1 divided by 3 x of n plus x of n minus 1 plus x of n minus 2. Is this stable? For bounded input, it is a stable system because the expression, all three instants of the input, present input, delayed input and 2 units delayed input, will also be a bounded quantity. So 1 divided by 3, if all three instants are added together for finite value, it will be 3m. So output will be equals to m, a finite quantity which will be less than infinity. So a system is stable system. The next system property we'll be studying is time invariance. A system can be time invariant or time varying system. A system is said to be time invariant system if a time delay or time advance of the input signal leads to an identical time shift in the output signal. Meaning, if the input to the system is delayed, output from that system should be delayed by the same amount of time as the input was delayed. And if the input signal to the system is time advanced, then the output from the system should also be time advanced with the same amount of time as the input was time advanced. Therefore, if x of t input is producing y of t output, then the delayed input defined by x of t minus t naught should result into delayed output y of t minus t naught. If these conditions are satisfied, then only a system is said to be time invariant system. Else system will be time varying system. Now this time invariance mean only the shift is in the independent axis. Either signal will be delayed or advanced. The overall shape, the expression of this signal will remain same. If the shape of the input remains same, then shape of the output should also remain same. Only shift should occur in time. If the input is delayed, output should also be delayed, and if the input is time advanced, output should also be time advanced. If these conditions are satisfied, then a system is said to be time invariant system. Let us consider an example. Y of t equals to sine x of t, where x of t is the input. Now to introduce time shifting, let us change t equals to t minus t naught in the input. Then the expression will be sine of x t minus t naught, which is equal to y of t minus t naught. Therefore, system is time invariant. Let us consider a discrete time example. Y of n equals to n times x of n. Now, if we introduce time delay for the input signal, then the output signal has to be y of n minus n naught, which is not in this case clearly, because independent variable has been changed only in the input signal. If you write the expression for y of n minus n naught, it should be n minus n naught times x of n minus n naught. So output is not equal to that. Therefore, this system is time varying system. If the output expression was equal to n minus n naught x of n minus n naught, then the system would be time varying. But here the expression is n times x of n minus n naught, which is not equal to y of n minus n naught. Therefore, the system is time varying system. The last property we'll be studying is called as linearity. A system can be linear or non-linear system. A system is said to be linear in terms of the system input x of t and the system output y of t if it satisfies the following two properties of superposition and homogeneity. It is simple. A system is said to be linear system if the system satisfies the property of superposition and the principle of homogeneity. If either of these two conditions are failed, then a system is said to be non-linear system. Compulsorily, both of these two conditions are to be satisfied. Then only a system is said to be linear system. Else the system is said to be non-linear system. Then the principle of superposition is, if we have two inputs, x1 of t and x2 of t, and x1 of t is producing the output y1 of t, and x2 of t input is producing the output y2 of t, then for a system to be linear, it is necessary that composite signal input produces the corresponding output. If we form a composite signal using x1 and x2, by adding those two, x1 of t plus x2 of t, then the output due to this composite input should be addition of the individual outputs, y1 of t plus y2 of t. So composite input should produce the corresponding output from the system. It is like if we apply each of these signals individually to the system, they'll be producing y1 of t and y2 of t individually. If we combine the inputs, then the outputs due to the individual input should also be combined together. Then only a system is said to satisfy the superposition property, which is required to satisfy the linearity. And the homogeneity property states that if input x of t is producing the output y of t, then whenever input x of t is scaled by some constant a, then the output from the system should also be scaled by the exactly same constant a. That is, if input x of t is scaled by a, it should result into the output scaled by the same factor a y of t. And if the system violates either of these two properties, principle of superposition and property of homogeneity, then a system is said to be non-linear system. So system is said to be linear if it satisfies the principle of superposition and property of homogeneity. Else it's a non-linear system. So to summarize, a system is said to be linear if and only if a1 x1 of t plus a2 x2 of t result into a1 y1 of t plus a2 y2 of t. Input, if input is superimposed, output, individual output should also be superimposed, and if the input is scaled, output should also be scaled by the same factor. Then only a system is said to be linear system. For example, y of t equals to m x of t plus c for c not equal to 0. Now this might be a linear equation, but is it a linear system? We'll have to verify that. Clearly, it is a non-linear system. Because if input is 0, if x of t is 0, y of t will be equals to c. 0 input is not resulting into 0 output. Instead, we are getting some constant c. Therefore, it is a non-linear system. 0 input should always result into 0 output. Now, to understand all of these 6 properties for this system, let us consider a problem. Consider a multiplier system. X of t is the input, and one of the input to the multiplier is a cosine generator, cos of omega c into t. So the total output of the system y of t is x of t cos of omega c into t. Now we'll have to verify all the 6 system properties on this system. Now the first thing, is it a memory system or a memoryless system? Because the output depends only on the present input, system is memoryless. For a system to be memory system, output should depend on previous value of the input as well. But here, system output is dependent only on the present instant of the input, so it is a memoryless system. Is it a causal system or non-causal system? It is a causal system. Again, output does not depend on the future values. Output depends on present value of the input only. Therefore, the system is causal system. Is it a linear system? Yes, it is a linear system. If input is decomposed into two parts, x1 and x2, and if they are scaled by a1 and a2 factors, and if both are multiplied to the cosine omega c into t, then we'll get a1 x1 of t cos omega c into t and a2 x2 of t cos omega c into t, which satisfies the principle of homogeneity and superposition. Therefore, this system is linear system. Now, is it time invariant or time varying system? Now, to verify the time invariance, we'll delay the input by substituting t minus t naught in place of t. So, transformation of x of t minus t naught will be equals to x of t minus t naught cos omega c into t, which is not equal to y of t minus t naught. Y of t minus t naught would result into x of t minus t naught cos of omega c of t minus t naught. Therefore, the system is time varying system because y of t minus t naught is not equal to y of t. Is it a stable system? Now, to understand the stability of this system, let us consider the input x of t is bounded. Therefore, we'll define x of t, or we'll consider x of t to be having a finite value m. For bonded input, system will be producing the bonded output. Modulus value of y of t equals to modulus value of x of t multiplied by modulus value of cos omega c into t. We already considered input is bonded. So modulus value of cos omega c into t will always be less than or equal to 1 when it is multiplied with the bonded value of the input. Output y of t will always be bonded. Therefore, the system is stable system. Next, we'll consider an integrator system. For the system t of x of t, which is nothing but y of t, equals to integration minus infinity to 3t x of tau d tau. We'll have to verify the properties of these systems on this. First thing, is it a linear system? Yes, it is a linear system because integration is a linear operation. If you apply superposition and homogeneity on this, if integration is divided between both the terms, we'll get a1 integration minus infinity to t 3t x1 of tau d tau plus a2 integration minus infinity to 3t x2 of tau d tau, which is nothing but a1 y1 of t plus a2 y2 of t. Therefore, the system is linear. Now, is it time varying or time invariant system? Let us substitute t minus t naught in place of t. Then the integral will be changed to integration only input has been delayed. Remember, delay in input should result into delay in the output as well. Now, will it happen in this case? We'll have to verify that. If the input is delayed, then the integral will be integration minus infinity to 3t x of tau minus t naught d tau. In the upper limit, we are not changing t to t minus t naught because only input has been delayed. You should remember that. And we'll substitute tau minus t naught as m. So the integral variable will also be changed. So the expression will be integration minus infinity to 3t minus t naught x of m dm, which is not equal to y of t minus t naught. Therefore, the system is time varying system. If it has to be a time invariant system, then the expression would be integration minus infinity to 3 times t minus t naught x of tau d tau. Clearly, this is not equal to y of t is not equal to y of t minus t naught. Therefore, it is a time varying system. Is it a causal system or a non-causal system? This system, the integrator system defined, is a non-causal system because the present output depends on present, past and future values of the input, because the integration limits are from minus infinity to 3t. For example, if we are verifying the system output at t equals to 1, then the limits will be from minus infinity to 3. Minus infinity to 0 corresponds to previous values of the input. T equals to 1 corresponds to the present instant input, and t equals to 3 corresponds to the future values of the input. Therefore, the system under observation is non-causal system. Is it a bonded input stable system? Now, to understand that, let us consider an input signal x of t defined by unit step u of t. U of t is a bonded input. If this is the input to the system, by substituting u of t and simplification, we'll get 3t u of t. Time t output is dependent on the variable t. T is the independent variable which will be ranging to infinity. As t tends to infinity, output will also tend to infinity. Even though input is bonded, output is unbonded. Therefore, the system is unstable system. And is it a memory system? Yes, clearly it is a memory system, because to get the output, we are integrating all the previous values of the input. The limits are from minus infinity to 3t. Therefore, it is a memory system. And is it invertible? Yes, it's an invertible system because its inverse operation, differentiation, exists. We might have to scale the input. We might have to perform some operations to obtain or to recover the input back, but the system is invertible system because the inverse system exists. I hope you understood all the properties of the system and the problems we have studied. If you have any doubts, you can contact me. Thank you all.